we need to detect clearly and we need to indicate to the coastline. Okay, to reduce the damage to the people and to the people. Okay, we need to give clear indication at the time of tsunami and for suppose there is a infrastructure in underwater cultural heritage monitoring is there. For suppose, for example, like there is a Dwarka city, there it is in underwater, submerged in underwater. Now we want to do the research. Okay, we need to do the structural health monitoring in underwater means that time also we require this sensor networks. Along with this, there are something like ocean medical research also is there, and there are some military applications are there. For suppose there are any intruder are coming under the water means we need to find out that intruder. Okay, and very recently this IoT is coming to the underwater. The name is like Internet of underwater things. There are some sensor nodes. Internet connectivity is placed in underwater. It will monitor some physical parameters. Okay, that is called underwater Internet of underwater things. To basically to we need these applications. Okay, how to get these applications? Okay, this one we can get by using the by constructing the sensor networks. Okay, basically this underwater wireless sensor networks is nothing but is consisting of several sensors and autonomous underwater vehicles that are deployed in underwater environment. What and that will communicate wirelessly, perform some collaborative tasks like underwater structural health monitoring or ocean exploration or ocean medical research or tactical surveillance. These applications need, that's why we are going to build the underwater sensor networks. When we go with the wired communication, that time there are some problems are like car is one of the problem. Another one is like if any damage happened to the cable and all means that time it is very difficult to reconstruct that. Okay, when we go with wired communication and underwater. Okay, that's why nowadays we are preferably using the wireless communications in underwater. That's why the name we use like underwater wireless sensor networks. Now, in that wireless communications, what are the different technologies we know? What are the different signals we can use? One is like radio signals we can use, optical signals we can use, and the acoustic signals we can use. When coming to the RF signals, the problem is here this medium is a conducting medium. To transmit the RF signals in underwater, then the energy is absorbed very highly. Due to that, the signals cannot travel for the longer distances. Okay, that's why the propagated long distance only at a very low frequencies only it can go. Okay, if you are changing high frequency, then the absorption is more from the underwater medium. Due to that, we are getting very limited range. Okay, and one more thing, due to the high absorption losses, we need a requirement for the large antenna and high transmission power like this. We need a large antennas and high transmission power is required to transmit the RF signals in underwater. Okay. Practically like high frequency, like if we are using 433 megahertz, the distance we will get is like 120 centimeters. Okay, when we are going with like Wi-Fi 2.4 gigahertz means the distance we can transmit the signals is just at 1 centimeter. Okay, these RF signals are limited to the very shorter distances. Okay, when we will use the optical signals, then the problem is we need high beam. Okay, we need narrow laser beam is required. That's too. These optical signals also are confined to short range like 10 meters. But within the 10 meters, it will do high data rate. Okay, due to the bandwidth available in optical communication, optical signals, we are getting very high data rate. Okay. Then the next thing is like acoustic communication. Acoustic communicators. Acoustic communications are you can travel for the longer distances in underwater, and when it is providing is very limited. When compared to the optical and RF signals, acoustic signals will travel longer distances the underwater medium. Okay. The range is up to several kilometers a second. The data rate we will get is like something around some 60 kbps in the range. Some few kbps we can achieve in underwater. Okay. That's why due to the disadvantages of radio signals and optical signals, we will preferably use acoustic signals in underwater medium. That's why from now onwards we are going to discuss with the underwater acoustic communications. We discussed wireless medium. In that we found that acoustic signals are most preferable for the long distances. That's why I need the communication for the longer distances. That's why we choose the acoustic signals for transmitting the data. Okay, that from now onwards, I am mainly sticking to the underwater acoustic communications. Okay, we are using acoustic signals. Then what are the issues? What are the issues available in underwater acoustic communications? The bandwidth we will get in underwater acoustic communications are very limited because these frequencies are in few kilohertz. Due to that, the bandwidth we will get is very few hertz only. Due to that, what is happening? The data rate is limited. Due to the limited communication bandwidth, the achievable data rate also is very limited. I think we know the Shannon capacity theorem. Capacity is mainly dependent on the bandwidth and signal to noise ratio. Capacity is equal to bandwidth into log 2 plus 1 plus SNR. If bandwidth is less, then the capacity we are achieving is very less. Okay, that's why with the limited communication bandwidth, we are getting limited data rate. And that too, one more problem is in underwater, when coming to the terrestrial, like ground wireless sensor networks, if you take, RF signals travel at the speed of 3 into 10 to the power of 8 meters per second. Okay. But when coming to the underwater, acoustic signals will travel at a speed of 1500 meters per second. Okay, acoustic signals in air, like ground, it will travel is like 300 meters per second. When you compare acoustic signals in air and ground, air and water means that time acoustic signals will travel better in water. But when compared with RF and acoustic means that time the propagation delays are very high. Okay, because it is the signals are traveling at 1500 meters per second. Due to that, if you want to send the signals for longer distances, it will take more propagation delays. Okay, the main problem is limited bandwidth and increased propagation delays. These are coming because of acoustic signals we are using in underwater. Along with that, underwater acoustic communication suffers with the multiple and Doppler. Here the sensor nodes are moving due to the current waves and all. Due to that, the sensor nodes are moving. When there is a movement in sensor nodes are coming, then there is a concept called Doppler spread will come. Okay. And something here bottom surface are due to the shipping or aquatic animals, due to that there is a multiple propagation is also happening. Okay, these all factors leads to the variation in temporal and spatial characteristics of underwater acoustic network channel. Okay, we discussed like limited bandwidth leads to the limited data rate. Similarly, here when coming to the reliability, this underwater have poor and channel characteristics. This will lead to a high probability of receiving erroneous data packet of the destination. Okay, to improve the reliability, actually researchers what they are doing is like cooperative communications. Okay, we are going to use the relay node to retransmit the signals to the destination. Okay, relay will help the transmission. That is called, we will discuss the scheme, what is meant by cooperative communication and the cooperative communication with the forward error corrections. If we will use some error correcting codes to remove some errors available in the data packets received at the destination. And there is one more technique like ARQ technique. If any the packet received at the destination with some errors means it will ask for the retransmission. Again, transmitter will retransmit the data packet. Okay, like the ARQ, cooperative communication techniques are used for improving the reliability. One more problem with the underwater acoustic communication is like energy efficiency. Why we need this energy efficiency means here the sensor nodes are primarily powered by batteries. Okay, these are primarily powered by batteries. Once if you deploy in underwater, it is very difficult for us to again recharge or replace the batteries of the sensor nodes. Whatever the battery available at the sensor, then we need to use more efficiently. Okay, we need to use more efficiently. If you see here, transceiver, transmissions and receptions only, it is taking highest energy consumption. Okay, that's why we need to reduce the retransmissions from the same node. Okay, that's why we can use the cooperative communication. Now, based on these issues, our design constraints are like I want to design some protocols such that to improve the reliability of the communication channel, communication thing. Then our another aim is to extend the network lifetime by improving the energy efficiency so that nodes can be available for longer time. Okay, it can be active for longer time. Then there are something underwater multimedia, underwater Internet of Things are coming. These applications require high data rates. We need to improve the data rate. Okay, we need to improve the data rate. These are the our protocol design objectives. Okay, my aim is like I want to improve the data rate for some applications. I want to improve the reliability. I want to improve the energy efficiency. Okay, before going to discuss with the schemes, we discuss the underwater acoustic physical layer channel. Okay, here I want to find out the signal to noise ratio. The signal to noise ratio is given by the equation number 1. Here, the SL is nothing but source level. TL is nothing but transmission loss. Transmission loss is nothing but like path loss. And NL is nothing but ambient noise level. TL is like if I am shouting here, after some distance, whether same amount of energy you will receive, there will be some absorption, some path loss are there. That is given by the TL. NL means there is something like ambient noises. Okay, for acoustic signals, there are some ambient noises are there. Those are called NL. And based on the directional antenna or omnidirectional antenna, this directivity index is decided. If it is a directional antenna means the signal received is more. Okay. PA is like for directional antenna, it is a plus 3 dB. If it is a omnidirectional antenna, it is 0 dB. How we are going to find out this source level? Okay, source level is can be find out by this formula, equation number 2. It is 10 log transmitted intensity divided by the reference intensity. The reference intensity is based on this formula, Q square by rho C. Okay, Q is nothing but acoustic pressure, C is nothing but speed of acoustic waves, rho is nothing but density of sea water. With that, we can able to find out the I reference. Now we will see what is IT. Okay, it is nothing but transmitted signal intensity. Intensity is nothing but power flow per unit area. Okay, in underwater there are two different types of scenarios are there. One is shallow water scenario and another one is deep water scenario. Shallow water scenario is like where depths are like few meters. Ocean depth is like few meters. Okay, there is in deep water, ocean depth is greater than few meters, like some 100 meters more than that we will consider like deep water. If it is like 10 meters or 20 meters, we will consider like the shallow water scenario. Now in shallow water scenario, if I transmit the signal, if the sensor node is transmitting about the signals means, then those signals are reflected back from the ocean bottom surface or and the top surface. Okay, the acoustic signals are reflecting from top and bottom. Okay, this is how this is leading to uh, cylindrical spreading of acoustic signals. Now we can able to check this one. If the transmitter is transmitting the acoustic signal, then top of the surface, ocean surface is reflecting back the acoustic signals and bottom also reflecting the acoustic signals. Due to that the spreading is like here is like a cylindrical spreading. Okay. Now accordingly, the transmitted power transmitted we can find out like area per cylinder is like 2 pi RH into transmitted intensity. Like that we can able to find out the power transmitted. Now when coming to the deep water scenario where the signals are not reflected back from the surfaces. Okay, we can consider this spreading like a spherical spreading. Okay. Accordingly, in deep water, the power transmitted is nothing but 4 pi r square into IT, or transmitted intensity. 4 pi r square is nothing but the area of the sphere. What we can understand is like from acoustic signals, the splitting in shallow water scenario is like a cylindrical splitting. When coming to the deep water, it is like a spherical splitting. There are two different scenarios are there, shallow and deep water. Now we found SL. Now we are going to discuss with the transmission power loss. If I transmit some power after some distance, how much energy loss will be? Okay, that is given by here transmission of splitting loss and absorption losses. Okay, due to splitting, there is some loss in there, and due to absorption of underwater medium, there is a some other loss, absorption losses in there. Now here K is nothing but spreading factor. This K is decided like K is equal to 1 for shallow water scenario and K is 2 for deep water scenario. And the area of M is nothing but absorption coefficient. Okay, the characteristics between shallow water and deep water is like the main thing which results the shallow water scenario and deep water is like the depth in kilometers. Here it is like equal to 100 meters. This is 100 meters to kilometers. Based on that things, here the transmission loss like surface reflection is there. Here both surface bottom reflection loss and sediment loss is there. When coming to the temperature in shallow water, temperatures are like 24 degrees and in deep water it is very low, 4 degrees. And when coming to the salinity, it is like 35.5 ppb, here 34.5. Coming to the splitting mainly, in shallow water, it is like a cylindrical spreading. When in deep water, it is like a spherical spreading. When coming to the density, it is like 1025 in shallow water and 1028 in deep water. Now, the absorption coefficient is given. There are several empirical formulas are there. What is meant by empirical means researchers will conduct some experiments. Okay. They will conduct the experiments. They will transmit some signals. After some distance, they will receive the power. Okay, power intensity. Based on that, they are finding the equation. Based on the experimental conductions, they will find the equations. Those equations are called empirical formulas. Okay, here the empirical There are different types of absorption conditions are available in underwater, like Shelikin and Mars formula is there, and Tom's formula is there for absorption coefficient. Here, Shelikin and Mars is given in the equation number 6. This absorption is mainly dependent on the frequency. Absorption is mainly dependent on the frequency and the salinity and hydrostatic pressure and depth of the version. This will decide the absorption coefficients. When you plot this one, if you properly see this one, if there is a increase in frequency, then absorption loss is more. This is indicating that high frequency signals cannot travel for a longer distances due to very high absorption losses are there. When there is an increase in frequency, the absorption loss is increasing. Similarly, when coming to the delta rates, for low, high absorption is there. Okay, this is coming because of the hydrostatic pressure, hydrostatic pressure. If that hydrostatic pressure is increasing, absorption loss is like 1 minus hydrostatic pressure. Due to that, for lower depths, we are getting higher transmission loss. Okay, the path loss available in lower depths is more. And when coming to the frequency side, higher frequencies are abbreviated of much in underwater. Now we will this figure represents the total transmission loss. Transmission loss we already discussed. It is a mixture of spreading loss and absorption loss. Previous figure we saw the absorption losses. Now we will see total transmission loss. It is a mixture of spreading and absorption loss. If you see the scenario, if for longer distances there is a high absorption is for longer distances. If source and destination is separated by longer distance, absorption is more. For lower frequency, only less absorption. But when you are doing higher frequencies, we get more absorption is there. Means from this we can understood one thing is like high frequency signals we cannot transmit for a longer distances because when you transmit that signals there is a high absorption from the medium it is there. High absorption from the medium. This figure is related to the shallow water scenario. This figure is related to the shallow water scenario. Similarly, for deep water scenario also, the figure is very much similar. Okay, for higher distances, we are getting high transmission losses. And when coming to the frequency, high frequency signals are having very high transmission losses. Or from this, we can understood that in both shallow and deep water scenarios, we cannot transmit the signal for longer distances because when you transmit high frequency signals, if the distance is increasing, there is a high transmission loss is there. Now we will discuss the third component that is like ambient power noise. Okay, on the receiver side, there are some environmental noises are available. These are the mixture of turbulence noise, tipping noise, and wave noise, and thermal noise. These formulas are like empirical formulas. Again, experimental conductance, they resultants based on the results, they frame these equations. Now here, turbulence noise is available only for frequency less than 10 Hz. Then shipping noise is available in between 10 to 100 Hz. This wave noise is available in between 0.1 kHz, 100 Hz, 200 kHz. And basically, this thermal noise is mainly located in 100 kHz. Okay, all these noises are called ambient noise power noise. when you are receiving the signals through your ear, there are some nearby, some other acoustic signals you are receiving. That is called ambient noises. Okay, those are like turbulence, shifting, wave, and thermal effects. If you see the graph, turbulence noise is like it is decreasing with increase in frequency. It is decreasing with increase in frequency. When coming to the shifting noise, high shifting activity leads to the more loss. Okay, high shifting noise, high shifting activity leads to the more noise. Moderate shifting leads to the medium noise, and the light is reduced. Okay, and when coming to the waves are creating some disturbance on the receiver side. Okay, high waves is giving more noise. Low waves are giving less noise. When coming to the thermal noise is given like this. Okay, there in these papers, what they did based on these frequencies, they approximated and they have given one formula like 50 minus 18 log f. Instead of using all these formulas, we can approximate the ambient noise like 50 minus 18 log f. The figure follows this one. The structure will follow like this. Like that, they have approximated this ambient noise power level. Now, this figure is mainly this is inverse of transmission loss and noise, ambient noise. If I am taking path loss as well as ambient noise, okay, at the receiver side, some noises are coming. Okay, along when I transmit some power, after some distance, there are some path loss will be there. Those are called transmission loss. We are taking the product of transmission loss and ambient noise. Now, if you see this figure properly, here for high frequency signals, the attenuation is very high. High frequency signals, attenuation is high. Here, very low frequency signals also is attenuation is high. Here, some in between here, we are getting less transmission, less this losses. The product of transmission and noise level is less here. Okay. For all the frequencies, we are not getting the same transmission losses. Here, transmission losses are mainly dependent on the frequency as well as distance. If frequency is varying, this product is also varying. If distance is varying, this product is also varying. Okay. Here, one conclusion from this figure is that very important conclusion is like all frequency signals won't get same transmission loss. High frequency signal will get very high transmission losses. Low frequency signal will get less transmission losses when compared to the high frequency. You know that whenever there is a channel here the kind of please understand that this transmission loss is mainly dependent on the frequency as well as distance. In many times in terrestrial communications, the researchers will consider that transmission losses are constant over triangle. But that same consideration we cannot able to take in underwater medium because here this transmission losses, this product of transmission losses and the ambient noise level is mainly dependent on the frequency and distance. Now we understood the underwater physical layer channel. Now we will see how to improve channel capacity. So my aim is like I want to improve the channel capacity. How to improve it? We propose NOMA-based cooperative relaying scheme for underwater traffic sensor advice. The first is we'll discuss scheme like direct communication. Direct communication is like From the source to destination, there is only direct link is available. Okay, so the data packet to the destination, if it receives properly, it will give the acknowledgement. If it is not receiving properly, again it will give the acknowledgement. Okay, if it is receiving properly, it will give positive acknowledgement. If it is not receiving properly, that time it will give negative acknowledgement. That time what source will do, again it will retransmit the data packet. Like this total more number of retransmissions, this node energy is losing. Okay, the node energy is losing due to that the network lifetime is less. That's why there is another scheme, that is cooperative relaying scheme or cooperative communications, which will exploit the spatial diversity. For suppose source is here, destination is here. In between source and destination, there is some relay node is there. There is a relay node is there. Now, due to the broadcasting scenario, like source node will broadcast the signals, the data packet will go to the destination. Okay. At the same time, in the phase one itself, that same data packet is received at the relay node. Now, if it is getting proper data packet, then it will give the positive acknowledgement. If it is not getting, if it is not getting proper data packet, that time what it will do? It will do the negative acknowledgement. It will get negative acknowledgement game means source will direct the relay node and transmit the data packet. Okay, instead of sending from longer distances, now we can you assume like this relay is somewhat nearer to the destination when compared to the solution. Now in the retransmission, we are transmitting from the less distance. Okay, here we are using multiple paths from here source to destination one path is there, source to relay to destination one path is there. This is called spatial diversity. That is the advantage in the cooperative relaying scheme. Due to that, the reliability is increasing. The reliability is increasing. But there is one more problem is there. One, one more problem is due to CRS, reliability is improved. Okay, we are able to decode the data packet, but the problem is data rate because here multiple retransmissions are there, duplicate transmissions are there. Due to that, spectral efficiency means bits per second. Spectral efficiency is nothing but bits per seconds per minute. Okay, that spectral efficiency is coming down. We need to improve that spectral efficiency. Nowadays, but then one more main Indian issues is like we already discussed, acoustic signals are getting very limited bandwidth. Due to very limited bandwidth, we are getting very less data rates. Again, if we use cooperative relaying scheme, then again data rates are reducing. Now I want to improve the data rate. How to improve it? We need, recently there is a one technique called non-orthogonal multiple access has recognized as the potential multiple access technique for 5G communicator due to its improved spectral efficiency. NOMA is considered as one of the technique which can improve the spectral efficiency. How NOMA will work means this figure one here is showing like it is orthogonal multiple access. In orthogonal multiple access, for each resource block, either that is a frequency or time or point, we are allocating only one user. In each resource block, resource block, you consider this as frequency. Each frequency, that bandwidth, we are only using one user. Here also one user, here also one user, here also one user, here also one user. In that frequency, there are no interfering signals are not there. But when coming to the non-orthogonal multiple access, in a single resource block, there are multiple transmissions are going on. How we can what create the difference here means the power allocated for the users are different. Power allocated for the users are very different. Very simple scenario we will understand. Like I am the transmitter. There are one nearby destination is there near me. Maybe you can take in the first row one person. Okay, you can consider beside me, beside very close to me, one more transmitter is there. I will shout it. This person also will shout it. That very near person, he can easily found that there is a signal like AV is coming simultaneously. Similar to that, here we are using same thing with the different power levels. I will shout A with the louder, he will shout B with the small. Let's power. We nearby persons can easily decode the signals in AV. How it is going to happen in the signals means there is one technique called successive interference cancellation is there. SCMC technique. Please understand this one. This transmitting node is transmitting the signals to the far user and the near user. Here, far user is having poor channel conditions. Poor channel conditions means high power loss. That's why this one is considered as a weak user. Nearby user have good channel conditions. Nearby user have good channel conditions. That's why we consider this one as a strong user. Okay. Now this transmitting node, what it will do? It will transmit the. It will combine. First, it will combine the signals of weak user and strong user by using superposition theorem. Okay, it will allocate some power to the weak user signal and some power to the strong user signal. Okay, this signal is given with more power because it is a longer distance in there. If you reduce the power, the overall absorption, that signal won't reach to the weak user. Okay, that's why more power allocation is given to the weak user signal and then less power allocation is given to the strong user signal. Now, what weak user will do? Weak user will consider the signal, his own signal, and he won't think about the strong user signal. Whatever it is receiving, from that it will decode its own signal only. So I show A, that longer person only can understand A. He cannot listen B because if I shout B with the smaller voice, he won't reach to me due to the transmission losses. But he can receive A only because I am shouting with more power. Okay, but near user, what it will do, it can receive high. What he is doing, first high power signal is first decoding. Whatever A is there, he will decode the first. Then that signal is subtracted from the whole signal and it will decode the B. Like that, the things will happen. This is called successive interference cancellation. First, it will decode high power signal, then subtract from the total signal, then whatever the remaining signals are there, from that decode the small power users like near user its own signal. Okay, this entire combination of superposition and successive interference cancellation is mainly available in the non-orthogonal multiple access. By using this only, we can able to implement the non-orthogonal multiple access. Okay, we understood that mainly CRS is a powerful approach in underwater acoustic sensor networks. But it enhances the reliability. But it is reducing the spectral efficiency. To improve the spectral efficiency, what we are doing, we are combining the NOVA with the CRS. With that spectral efficiency as well as reliability is increasing. And there are some papers, they have used only perfect CSI. Okay, which is also too realistic, idealistic assumption in advanced acoustic sensor networks. We have also considered imperfect CSI in underwater. See, here, see this NOVA cooperative design scheme. Here, source, this is source node. This is node B. Node B is like a four channel conditions are there. You can assume like it is in form. And this G is node G is like a near node channel conditions. Okay, what we are there is a x1 of t and x2 of t. Two symbols are there. I want to one is intended for the for user. Okay, here both the signals are intended for the for user. I need to transmit x1 and x2 symbols to the for user. What we are doing, we are root over alpha pt. Alpha 1 pt is given from the for user. Root over alpha 2 pt is given to the near the x2 symbol. We transmitted the source will broadcast the signal. Then source will decode only x1 symbol. Source will decode x1 symbol. G node, the near node what it will do, we will decode the back signals by using successive interference cancellation. Once it is decoded all the signals, it will transfer the x2 symbols to the far node. Okay, we will see the mathematical modeling. How with that we can able to find out the channel capacity, energy efficiency, and outage output. But here the G node receives x1 symbol and x2 symbol. x1 and x2 are transmitted with this amplitude root over alpha 1 pt. Here x2 is transmitted with root over alpha 2 pt. And when you transmit some signals in wireless, for suppose x1 you are transmitting means while receiving you will receive a signal y of t is nothing but h into x of t plus 9. Okay, h is the channel coefficient, x is the symbol plus some noise used. So here h is the channel coefficient. So from source to good node, that node is strong near node, the channel coefficient is this one. And there are some imperfections. Like if we are unable to find out that channel state information means if it is imperfect channel state information, then some extra channel coefficient, channel information is coming. Okay, then this is the transmission login. This is the signal received at node G. Okay, the estimation of HI at the receiver is this one. Okay, now from this at node G is a near node. It will decode the both signals x1 and x2. Here, by finding the x1 symbol, this is the desired power. Remaining is the interference power. The desired power is alpha 1 mod hs square. And the remaining is the interference available in this. While decoding x2 symbol, this is the what near node it will do. First it will decode the x1 symbol, then it will go for the subtraction. Okay, while if it is unable to find out a1 the x1 symbol properly, there is some that also we are considering here. This is x2 power is the desired for decoding x1 symbol. Then remaining is the this one equation number 9 will give the signal to interference noise ratio. SINR it will do. Okay. Similarly, the signal received at the node P from node P is like the power node. That is given with the equation number 10. Here, HSP is the channel coefficient from source to the far node, and there is a transmission loss for source to far node is the. Then this is the broadcasted signal, and there is a noise available at the node P side. It is going to decode the x1's work that is given with equation number 11. Now, in the second transmission slot, it is transferring the x2 signal. Okay, and relay. Okay, that is given with the equation number 12. This is the relay. What node P is doing in the first time slot, it is in the first time slot, it is getting the signal from the source to far node. And in the second time slot, it is getting the signal from the relay node to the far node. These two signals, it is combining by using diversity technique. The diversity technique we use here is like selection diversity technique. Okay, when you are receiving two signals, in that whichever is having maximum SNR, that we are considering. Max or channel max of this SLR, comma this SLR. Okay, this is coming in the first transmission time slot, this is coming in the second transmission time slot. Now we are going to find out how much data rate we achieved. Okay, achieved with ergodic rate for X1 symbol. That is given by equation number 14. Here, ergodic rate is the average channel data rate over the time. Okay, that we can able to find out by using the expectation of this one. Okay. Now I need to find out the expectation. How we can able to find out the expectation? Expectation is nothing but integral minus infinity to infinity x to fx of the x. If I know the probability density function, then I can find out the expectation. Now my aim is to find out the probability density function. Okay, here we have in the previous equation we have this one log to 1 plus minimum of signal to noise ratio from source to the far user for x1 symbol, source to the near user for x1 symbol. Okay, now what? Already we found the SNRs. That SNRs we are substituting in it. We know. Now SNRs is substituted. This is the expression. What I am doing, the numerator whatever is there, I am bringing to the denominator. This also into the denominator. When I bring this one mod HSP square gamma SP to the denominator means here these two will get cancelled. Here it will become like psi SP by mod HSP square divided by gamma SP. Here also A1 if I am bringing mod HSP square gamma SP to the denominator set means then these two will get cancelled. Here it will come in the denominator. Okay, denominator to the denominator it will go. Now, you please observe here A1 divided by A2 plus something. Here also A1 divided by A2 plus something is there. Now I need minimum of this. Minimum is mainly dependent on this. Minimum is mainly dependent on this one. Okay, I can write the expression like this minimum I can bring inside A1 by A2 I am taking outside. Then minimum if I am bringing the expression is like this. Okay, then after performing log A by B, log A minus log B, I am getting this equation number 16. This is the equation number 16. Now, what we are going to do is, I am just finding the probability density function for this minimum of this one, these two. Okay, first we are considering this one as the random variable u and this one as the random variable b. Okay, here mod HSD is a rate limiting coefficient. Mod square, okay, mod square is following the exponential probability distribution. It is a very well known in wireless communications. That same thing we use and we found the cumulative distribution, yeah, capital FU of it and capital AP of. With that, we know V and U. Now W is nothing but minimum of U comma V. When there is a minimum is there, then the probability distribution is like this. Equation number 17. Okay. Similarly, we need one more also. This second one. We found this one. This is W, and we are getting this one as capital X, random variable capital X. Capital X is nothing but A2 into W. That's what we considered. Here capital X is a random variable that is nothing but A2 into W. To do the random variable transformation, you will get effects of this. By using these two, FW of W and effects of X, we can able to find out the CX one. Okay. Here, this is the one I need to find out. My channel capacity is nothing but this equation number 18. Directly finding this integration is difficult. What we are doing, we are using some mathematical, some approximations we are using. Based on these two approximations, we found the analytical expression as this one. Okay, CX1 over the bandwidth, the lower frequency to upper frequency, whatever is there, is given with this equation number 19 and 19. Here, why we are using integration? When you taking terrestrial communications, their capacity is nothing but bandwidth into log 2 plus 1, log 2 into 1 plus SNR. But here it is the integration. Here it is coming like integration. Why we are getting integration mean? Here transmission laws are mainly dependent on the frequency. We cannot consider same transmission laws for whole over bandwidth. Due to that, we are getting the integrations. Okay, this is the way to find out the analytical expression for CX1. CX1 is the achievable channel rate for simple X1. Similarly, we are finding the simple X2 also. Similarly, we are finding the simple X2. The equation 20 and 21 will give the channel capacity for simple X2. Based on these equations, these are some of the parameters we have used in simulation purpose. Okay. See here, we have plotted the ergodic rate with respect to distance between the source and destination. Here in x-axis, distance we have increased between source and destination from 100 meters to 1.5 kilometers. When there is a distance increase, the channel rate obviously is decreasing because the transmission losses and absorption losses is increasing. Okay. Here, we assume this. We have taken imperfect CSI also. When there is a increase in imperfections, if we are unable to find the channel scale information properly, then okay. Very good. Control changes. Similarly, here the near node is using connectivity problem translator. When it is decoding power user signal, if it is not decoding properly, then it is the connectivity difference. If near node is not properly decoding the first symbol, there are some it is not properly decoding. That time we consider some imperfect SAC we are considering. Okay. If there is imperfect SAC, again the water and over the signal, and it is imperfect SAC that is increasing, whatever the that is also. Now in CRF, where the real one. We consider real one nearer to the is one case we consider it is nearer to the source. In another case, we consider it is nearer to the far node. Okay, we consider total two nodes, two different scenarios. One time the node is nearer to the source. One time node is nearer to the far node. Okay, in this we are getting means near node is nearer to the source. We are getting better performance when compared to the node is nearer to the far node. Okay, we have considered something like shipping and wave noises and that. We consider all this shipping and noises, and based on that we have plotted when there is a increase in shipping and waves, then the transmission losses is more. So that again we consider differentiate the ergodic rate is available in NOMA CRS in underwater protections analysis. Okay, basically what our observations are like the performance of NOMA based CRS for UASN is analyzed under the imperfect CSA and the imperfect SIC. The results show that NOMA CRS can include ergodic summit compared to the conventional CRS, but the results show that the performance of NOMA CRS can be improved by placing the relay node near to the source node. That's what we understood. If the relay node is here, then we are getting better data rate, channel activity rate. If it is nearer to the far user, that then we are getting less performance. Then high speed winds, the high shifting activity severely degrade the performance of biomass gas. These are the observation we got from published in ITV Access. Then in the next work, we will it is like full duplex cooperative relaying scheme. This one we can discuss after the. Again, we can join. You can take 10 minutes break. Only 10 minutes. Okay. Yeah.